Okay, so before we went to the algorithm, we have been trying to maintain. We would like to maintain connectivity in streaming setting where edges are both inserted and deleted. But even before we went there, we asked a slightly different communication problem, where there are n players and each player has an adjacent has one row of an adjacency matrix, and they would like to communicate some small sketch of their adjacency, like one row of adjacency matrix, such that they give only n polylog information, and they are able to, and the central player is able to check whether the graph is connected or not at that point, looking at those sketches. And as I told you that in sketching, a sketch is an algorithm dependent object, right? So what we did first, that we decided which algorithm we are going to apply for our connectivity algorithm, and we plan to apply what is called Burovka's algorithm, which basically select an every edge incident to it arbitrarily, and for each connected component then it again selects an edge, and you do it until nothing no longer possible. And during the break, Venkatesh had a observation which says that why do we even think that n log n object is even sufficient. So if you notice that there are only log n rounds, and each log n rounds every vertex needs to care about just one edge which is incident to it, right? Because he only picks up one edge incident to it. So it appears that only somehow n log n edges are sufficient, right? We showed the bound of 2n, but if you think like for every edge, it seems that just log n edges incident to it are important. But the problem is that which log n edges are incident to it is not clear, because as we go further down, the which connected component it will belong to, that will determine which log n edge that could be interesting to him. Do you understand what I'm saying to you? Right? Imagine a suffer or the journey of a vertex. He is alone. He belongs to a component, right? He belongs to another component. He belongs to another component. Somehow, there are log n vertices outside of his journey. If I knew him, then I could only just keep this set of neighbors, which is like roughly at most log n, and I could just give you that, and then you will be happy with it. But we do not know how this algorithm is going, because this algorithm proceeds by arbitrarily just giving out an edge. Okay, and this is where some randomization and those kind of things will come into picture and will take care of many of these issues. But just to let you know, so now you notice that the way the Burovka's algorithm works is basically tries to maintain for every connected across any cut, it tries to keep an edge, right? So to maintain that kind of notion, we introduced the notion of sign vertex edge incident vectors. And what is the sign vertex edge incident vectors is basically you have n choose 2 length vector for an edge, and if you look at a vertex, I look at his neighbors which are forward and which are backward, and if you look at his list, for all these neighbors he puts -1, and for his forward neighbors in some sense he puts 1. So that's all that is happening in this. And what property it had? The property it had, which is going to be useful for us, that if you look at any set S, and let's sum up the vectors for the vertices which are contained inside S, then look at the support of this vector, then each non-zero element in this vector represents an edge which are going across, right? So this is why it is an important thing to have. Okay. Now, what do we need and what do we need from this algorithm? Okay. Suppose you know, right? Now imagine yourself that the person needs to send this matrix, send a sketch of his row to the central player, right? Now everybody can only send polylog n bits. So somehow he needs to do some sketching of his list and send it, so that when he runs this algorithm, right, this central player runs this algorithm, he is able to produce an edge whenever it is required, right. So basically what we need, if you notice what we need is, so here is your vector x, okay. I want to reduce this length to some x tilde somehow, right, do some magic, okay, magic, get x tilde. And what property do I want from x tilde? Let us try to abstract out the property what we need from x tilde, okay. So suppose given this x, I have produced this x tilde, and this x tilde has been, so this x tilde has been, will be given to the central player C. Now what I want from x tilde is the following property, okay, that if there is an index in x, so x is a like n length vector, like some length vector, okay, n length vector, okay. If there is an index in x, so suppose this is an index that has a non-zero entry, then by looking at x tilde, we are able to recover an index and a value of x that is non-zero, right. So what I am saying, given x, I will look at x tilde, and what is the property of this x tilde? Suppose x had some non-zero entry, if all are 0 then I do not care, then by looking at x tilde I am able to return to you an index in x and a value at that x which, right, value at x which is non-zero. I am not telling you that I will return you this particular or this particular or this particular, I will be able to return you some index which is non-zero. Now imagine that if I had such an object, right, and x tilde was very, very small, then how will I implement this algorithm? Every guy will make his x tilde, pass it to the central player, right, of his list, right. Now first round is very clear, right, I mean if I had any one, right, then this x tilde, I will look at this x tilde, it will have, by looking at this x tilde, how we look at this, it is a property, but if I can look at this x tilde, I can extract an index and the value, and I know there is an edge from here to here, because I have pre-decided, oh this index, if I give me 10th index, it represents vertex number 1 and blah, right. Looking at this index, I can tell you which edge it is. This is why we did n choose 2, because this actually fixes. So what is this? 1 2 1 3 1 4, like what is, how did you do 1 2 1 3 1 4 1 and 2 3 2. So if I told you 50, if I knew the number of vertices and if I knew the index, I knew the edge, right, I knew the edge, right. So I knew what edge is there, and if it is non-zero, it means that edge is present in my graph, whether it is 1 or -1, it does not matter, okay. So if I could do something of this nature, it will be great, but given x, I have got x tilde. X tilde can only talk about x, right, x tilde can only talk about x, but when we do algorithm, we would like to know not about just x, but about some subset of vertices, which ideally we would like to, then we would ideally like to would have x, x1, x2, x3, x4, x5, sum them up, right, sum them up and then look at their x tilde, but we do not know which components it is, right. So hoping that x will give me also some like x tilde corresponding to subset of vectors and sum them, that looks like too much. And that is where we will try to use the linearity of these matrices and see how these things are done, okay. Okay. So now we have gotten to the point where I will need to introduce what is called L0 sampling, my favorite term which I have learned. I will not talk about L0 sampling in details today, but on Thursday I will give you a whole one lecture on L0 sampling, how do you implement it, and what is called one sparse recovery, k sparse recovery, because that is going to form a very basic tools in our understanding of sketching algorithms, okay. So I'm going to use the following lemma. So here's a lemma. This is also called L0 sampling. So why it is called L0 sampling is that look at your vector x, okay? Okay, I would like to suppose there are support, I would like to output one of these values with probability 1 over support of x. Like, so look at non-zero entries in this matrix x. So that is defined by, what is support of x is the number of places, like support of x is I, x of I is not equal to 0. So this is basically support. So on its supports, I want to be uniformly at random. Right? I allow little bit of gaps here and there, but this is what means L0 sampling, is that I would like to return to you one of the indexes with probability 1 over the support of this object, okay? And we will do in this format next time, okay? But let's learn this lemma in a way which will be useful for our algorithmic purpose. So what are we saying? There exists a random matrix, and I will construct this random matrix to you. A, in what is the dimension of this matrix? Is R big O of log square n times n, okay, such that for any x in R to the power n, okay, R to the power n, with probability at least 1 minus 1 over n to the power c, okay, we can learn I comma x, I comma xi for some xi not equal to 0 from Ax, okay. So what does this tells us? So I have a random matrix A of small dimension, right? So I have a small matrix A, right? So what is the dimension of this matrix? Look at this, right? Let's look at P, okay? So P cross n, now you multiply this matrix with x, whose dimension is how much? N cross n. So what vector are you going to get? Some x tilde, and what is the dimension of this? P cross 1, right? And what does it tell us? That for any x in R to the power n, with probability, some very good probability, we can learn Ixi for some xi not equal to 0 from Ax. So looking at x tilde, which is nothing but Ax, right? I can recover an index and its value of x which is not equal to 0. This is exactly what this lemma tells us, right? But what is the dimension of x tilde, right? What is n for us? N is like number of vertices, right? So this is going to be some order log square n size vector, right? X tilde has dimension is log square n times one dimensional vector, right? So I could have a very huge, no, so we are going to apply n is going to be n choose 2 because we have this long vector, but log square of n choose k is also some big O of log n, so that doesn't matter, right? So if we are going to throw this matrix, going to apply to x, and we are going to get some x tilde vector, we are going to give this to the algorithm, okay? Okay. Like let's write down some useful properties of this, okay? We'll prove this. This is not very hard. So suppose we had multiple vectors. Multiple vectors, x1, x2, right? And xt, then what can we say? Then we can determine non-zero entry for everyone from ax1, ax2, dot 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 axt, right, with probability at least 1 minus delta. Do you see why? Probability that the first guy fail is 1 over nc, right? So you have to choose these things appropriately. So, but if you apply union bound, what will happen? You will fail for one of these guys is bounded by t times whatever the, right? So if I succeed this with probability delta, right? So if you succeed with 1 with probability 1 minus delta, then if you apply union bound, you're going to fail on at least one of them is upper bounded by delta times t, because either I can fail on this or this or this or this. So now by union bound, what will you get? We will succeed with probability 1 minus delta t. This is basically just union bound. Okay, and this is an important thing to remember, that this is, we can apply union bound because we failed with this. So independently, if we do these kind of things, then we can apply. Second is linearity, and this is very important for us. Linearity. What do you mean? Okay, suppose you are given ay, okay, and az, or suppose you are given ax and ay, okay, we can find non-zero entry of x plus y from what? Non-zero entry from, say, z equal to x plus y, right? Why? We can find non-zero entry of z given these two. You know why? Because look at a z. What is a z? It is a applied to x plus y, right? Now a is a matrix. So what is this? This is same as ax plus ay, right? So if you are given ax and even ay, I can add them up, but that is a applied to x plus y, which is a applied to z because of linearity, right? So if you give me this, I can also get a non-zero entry of z, which is a vector which has been got by summing them. And that just follows from the linearity of these matrices, right? If you had some non-linear object, then you cannot say this. What?
So A guarantees that I will have one, if X has a non-zero entry, the vector that I'm producing will have a non-zero entry. Right?
Fine.
And AY is also so. But so suppose your A is non-zero entry is some plus A and AY non-zero entry is minus A. Then your AZ non-zero entry becomes 0, but they might have other non-zero entries which will give a non-zero entry for this.
So it better have more objects. It's not deterministic, right? It better have more objects then, right? Because what could I do? If I knew x plus y, I can apply a to x plus y, no? And what am I guaranteed? If I apply x plus y to a? Exactly. So I'm doing the same, no? But I know ax and ay.
Just guarantee that you will have one non-zero entry of in AX, right? And one non-zero entry in A1. And now when you are adding AX plus A1, these two entries can cancel each other.
A is a random matrix. It has lots of properties. Okay? If I applied the same A to this x plus y, what am I going to get? My matrix is same, A. Look, I have not changed the matrix. if I applied this, does this matrix have this property that I will get if there is a non-zero entry in x plus y, right? Then this matrix is no different than this matrix, right? After I have selected A, this is not a deterministic procedure. So if this guarantees you, why shouldn't this guarantee you? It's the same multiplication. Did I change the matrix? Then yeah, it might cancel out, but that will happen with very low probability, right? Of course it can cancel out. There is a term here with high probability. Okay, so now we have all the objects ready. Okay, so what will player sense? Okay, so player sense, this is what players sense to the central player. What will they send? All these players P1, P2, Pn, what should they send? Look, the guy knows his vector, right? His vector. Then from here he can create x1, he can create x2, he can create xn, right? This long n choose 2 vector. Now he can create, look, it's a random matrix. There exists a random matrix with these properties, right? So he picks up his random matrix and sends it, right? Okay. No, I just decided to keep one because what is it? There exists a random matrix such that for any x this property holds. There exists a random matrix A such that for any x this property holds. So I have the same random matrix with respect to x1 also this property holds. With respect to x2 also this property holds. With respect to xn also this property holds. Okay. Look, I have not done analysis, right? This is what my algorithm does.
No, but so like these players can't communicate. So like suppose player P1 found some random matrix computed by some procedure. This random matrix, the player P2 will compute his own. So
Like there exists such an object. I told you they have a supreme power and this and that. Somehow they got hold of the same A. It doesn't matter. Of course, they can make their own matrix and compute, and we'll get to that. I mean, but it doesn't matter even if they would have done with the same matrix. The property of this matrix is you give me any x. Look, there exists a random matrix A, so I fix this random matrix A. And what is the property of that random matrix? That one random matrix. You give me any x, I am good with respect to that x with very high probability. Okay? But you are right, they don't know. So maybe if you really wish to compute these A's, you can compute them differently. But I don't want to compute them differently at this point of time. Okay? Yeah. No. Why? I mean, I can compute any round after this, right? No, we will use, no? We will use. Yes. So now C has all these guys, right? So A1 x1, A1, sorry, a x2, a xn, right? Let's call it x1 tilde, x2 tilde, xn tilde, right? Look, I mean, it'll grow and develop when things do not work out for each other. But if I'd have been simplistically, this is exactly what I will try to do. Now I want to run this algorithm, right? So first round is very easy, right? Like, look at every vertex. I want to run this algorithm rather than asking for each node select an edge incident to it and arbitrary. Say, hey, let's select x1 arbitrarily. How? By looking at x1 tilde. And what does this lemma tells us? What does this tells us? That look, with probability at least we can learn. So we can learn this, right? Forget about what is the running time of that algorithm, because this guy is super powerful. All he cares about that they have indicated to him only x1 tilde, x2 tilde and xn tilde. He doesn't even know a. He doesn't know a, he just knows x1 tilde. You have to understand that this guy does not, he just sees x1 tilde, right? But looking at x1 tilde, there is an algorithm which can recover and x, right? So he applies this here, okay? So now I have some connected component, I have applied this. Now what do I do in round T, right? In round T, suppose we need an incident edge corresponding to incident S from a connected component S. Right? At this point of time, he needs to compute an S. He needs to find this. Right? This is what he needs to. How will he find it? All he has is x1 tilde, x2 tilde, xn tilde. Right? Okay, fine. So suppose J in S, right? He sums up these object xj tilde. This is what he does. But what is this? Let's write down. This is nothing but summation j in S a xj. By property xj tilde, and this is where I am going to use a, right? So if you have chosen this appropriately, I can do this, I can use the same matrix A, no? By union 1. So why are you worried about it? What does this tell you? Look, you were right. Like, oh, you are going to use, but fine. But I told you, right? I will have good enough probability that even if I use the same matrix for all the n guys, I will be good enough. If I put, say, n to the power 1000, right? I only want them to be good for n vectors. Okay, for example. What? What?
So somewhere we have to use linearity.
We'll use here.
Yeah. And for that, I thought A should be the same for all.
Yeah, so A, that is why A is for the same player, right? But your question is like, but when I look, but I'm saying the same A can be good for several players because I can boost this probability good enough that I can apply union bound to be good for lots of objects for the same. This is why, right? Why A is not good for this? Why? Because what did this say? You are right. This says that this is good for one guy, right? But I want this to be good for blah guy. For each of these guys, he is good with this probability. But we would like that he is good for all this, and it's an and. This is why we need to do this, right? Because otherwise we will be sunk. Okay. But now we know this is this. Okay. But this is a linear guy. A is a linear matrix. So this is, I can take A out. And what is this A applied to this? What is this? What is the vector corresponding to XAS? Let's write down. XAS, I define the vector as summation J in S xj. Now what is the property of XS? is that if you look at the non-zero entries, they precisely correspond to edges which are going across. So if I have this, what can I recover from here? I can recover from here an edge which is incident to S, right? And I can do this because A is linear, otherwise I cannot use this. This is where I use the fact that my matrix A is linear, like my sketch is linear. Okay, so okay, so now this the same A needs to be good in the first round, same A needs to be good in the second round, same A needs to be good in the third round, and blah blah. So we also have to compute that probability somehow, right? Because we are doing lots of computation and this A needs to be good for all those computations. Okay, you have to be like, we have to keep this in track of mind that if we want to succeed with good probability, then we have to take care of all these things, because lot of things are happening now. Look, it needs to be good with some, it needs to be good with this, it needs to be good with that, right? So for him to be good with the sum, he needs to be good with individually here, right? And these are like too many objects could be happening. Okay. Okay. So this guarantees, what are these guarantees? That we can identify, this guarantees that we can identify a non-zero element of XS. Okay, so this is my whole algorithm. Okay, so what does player select? They have this matrix A, the same matrix A, and they apply to x1, they got a small vectors, they pass this small vectors to this. Now the central player needs to check whether the graph is connected or not. He runs this particular algorithm with these small sketches. That's it. Okay, and two, and hence, okay, okay. Any question? Okay. Hmm? 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 Three things. I want x to be good, y to be good, and I want x plus y to be good. So there's just three vectors. Apply this with three vectors, no? And apply union bound. What do you want? I want this thing to hold with respect to x, y, and x plus y. No? So of course it will held with 1 minus 3 delta. Okay. But it's, let's try to do probability computation and let's see what happens. Like, even if this is given to us, okay, how many times do we need to succeed if I am going to use the same A? How many times do we need to succeed? Hmm? Why n times? Look, for how many vectors do we need to succeed, right? It's the same thing as saying that how many vectors do I need to succeed? And when you apply it second time, you need to succeed second time. Maybe it's the same vector. Why 2n? it is, look at the component. If you sum them up, you again want to be true with respect to x1, x2, x3, x4, x5, x6, and then their sum. It's not edges.
Yes, so in the previous round you have said that it is true with x1, x2, x3, x7.
Yes,
In this round you have to say that this is also true for this sum.
but that sum depends on again x1, x2, x3, x4, x5, which anyway, so think about it. Okay. Now let's try to understand that how does this work, and that will give us a bit more understanding. Look, it's not obvious. This is fine that this algorithm is going to implement itself like this, but why this algorithm is going to produce like check connectivity or non-connectivity with high probability, it is not very clear, right? If all I have given to you is this, I know that linearity will imply this. For us to apply linearity, we need to apply with the same matrix, otherwise we cannot talk about linearity, okay? But notice one thing, we could change what A to apply in each round, because linearity in that round depends on the matrix which we use. So for example, x1 could have sent not one AX1, it could have sent, say, I choose some A1, A2, AT, T matrices randomly chosen with the same property. So I give this guy A1 x1, A2 x2, A3 x3, sorry, x1 x1, AT x1. I could give it to him and say, look, this sketch you please use it in the first round. This sketch you use it for the second round computation. This sketch you use in the third round computation. Now these are independent objects. So now what I have done, I have made sure that these AIs are independent in each of the round, right? Because the AI which I am going to use are independently chosen this random matrix. So I could do that, right? Because then also I can pull this out. Because if I am in the tth round, what will be this? Say t x tth round, and it is say ATXJ, right? So AT can come out, and I can apply linearity, right? So so what I'm trying to tell you that he's right to apply linearity. We need to use the same matrix, but we could use the same matrix but we are still allowed to use different matrices in different rounds, right? And that is a very helpful thing to use and do, because then each round becomes independent of the previous round, because the matrix which you are using are independent. Okay. Okay. And also why it is important to know this is, suppose I would have been doing distributed algorithm, then I would have been just doing each of these objects at different places with different AIs. Okay. Okay. So now let's go back and let's try to understand this algorithm a little bit, and then we'll come back and analyze this algorithm completely. So this is where my question came last time, was that suppose we are given a vector x, okay, it has exactly one non-zero entry. How can we recover this? And its index. So our idea was last time is that, okay, fine, there's exactly one non-zero entry, right? So our idea was that, okay, fine, let's take 1, 1, 1, 1, 1, 1, 1 matrix and multiply this with x, okay, this matrix. Now, x could be a very large object, but this vector I multiply is just one entry, right? It's just one entry. And what is this? It is the value of that non-zero object. Because it is like, what is this? This is, yeah, this is 1 cross n, n cross 1, right? 1 cross n, n cross 1. So this is 1 cross n entry, which is sum of these things, right? What is this? This is basically sum of xi, I in x. Basically, this is the object which it contains, right? So this gives me a value. But if I wanted the row number, what will I do? Right? So you take this and what you write? 1, 2, 3, dot, 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 n, and x. What is this going to give you? This is again going to give you a single entry, but this is going to give you a summation I going from 1 to n, I xi. Now, since it is a single and I been guaranteed that there is only one guy, so what is my index? My index is, suppose this is A and this is B. So what is my index? A by B, right? My index is A by B. Okay. So this idea is going to form our basic core. And now you are no more guaranteed this. But somehow we would like to use this idea to capture the whole thing. Okay? To capture the whole thing, we will try to do this. And imagine if I told you that, well, there are just log n entries. Suppose I told you somehow that x, like we have some upper bound on x, how many entries are x? Okay? So let's just ask ourselves that, suppose I knew that x is like log n, okay? Okay? So support of x is log n. Suppose someone came and told us, okay? And what I want to do, I want to multiply with a row, okay? I want to multiply with row, such that if I multiply this, what is the property I achieve? Like I get some non-zero entry, right? I am saying this is, look, so when I multiply, what am I going to get? If let's look at this, if I multiply this. So suppose let's call this A1, A2, AN. So what is this multiplication? AI, XI, I going from 1 to n. Okay? I would like to choose AI in a way that if I look at this sum, it has extracted exactly one non-zero value. Right? What I mean by this? So suppose I had one at this places, then the way I have selected AIs, it like suppose this is a second place, third place, fifth place, seventh place. So second place I have somehow set AI to be 0. Oh, third place I have set it to 1. Then I have set 5, 7, 9 to be 0. Then I have extracted exactly one entry, right? The way I have extracted here. So suppose somehow I can choose my X in a way that whatever may be the number of entries you are given to me here, say log n for example, I will be able to extract exactly one entry, then I'm great. Right? Because then what can I do? I will apply this, I know exactly the same entry, I apply the same trick as this, I will extract the same guy and I multiply A by B and then I know the value and the index. Do you get what I'm trying to say? Okay. So suppose I pick this AI slightly nicely, okay. How do I pick out this? So I am going to set AI to be 1 or 0, okay, with probability okay. So I am going to set it 1 or 0 with probability two power log of n divided by n by log n say plus 1. So how many entries are here? How many entries are non-zero here? Roughly log n. If I removed plus 1, I would have had roughly log n. Expected number of ones here will be like roughly log n. Right? What? This is log n by log n. So with probability 1 over 2 to the power log n minus log n, right? Right? So how many number of entries, what is an expected number of entries which will be non-zero here? It's roughly going to be log n, because this is how I did, right? N by 2x equal to log n. I chose, right? So what is n divided by this is exactly log n, because this is exactly how I computed, right? So what is the probability that number of entries are non-zero here? Like roughly log n, right? So now it's like if you have roughly randomly chosen log n guys, and there are some roughly log n guys, what is the probability that, I mean, more than 2 people are going to collide? It's going to be a very low probability. So this is exactly what I'm trying to capture, is that, okay, so I don't know how to deterministically construct these vectors, but maybe I can construct some sparse vectors in a way that randomly, that when I multiply them, it actually captures exactly one place as 1, and that's it. So this idea is called geometric sampling, okay? So what I do, I will do a geometric sampling. So this is like making 1 over 2 power 0, selecting an index with probability 1 over 2 power 0. Second, I will do with probability 1 over 2. Third, I will do with probability 1 over 2 power 2, and blah blah blah, and so on and so forth, okay? Okay. So you get the idea, right? So idea is that if I randomly select something where number of entries in my row and number of entries here are same, where randomly selected object, chances that they will collide, and this is where now we start to think hash functions, that if they will start to collide two people, is very low. Okay, we'll make all this formal and prove it formally. Okay, so here is my construction of this matrix A. Okay, it will not be sufficient. Okay. Okay, but it will have this intuition. Okay, let S0 S1 dot 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 S log n be a random subset of 1 to n, okay, where each element in Si, okay, where each element in Si is chosen with probability 1 over 2 to the power I. So 0 means 2 power 0, like this is like really all around. So now if you look at this vector, look at this matrix, what is this? This is a matrix where you will have 1, 1, 1, 1, 1, 1. Next time with probability half you are going to put 1 and 0. So here roughly I have all the n. Expected number of ones here is going to be n by 2, n by 4 and dot 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 till you become. So this is what I meant by geometric sampling, is like, okay, I'm reducing, right? So number of ones are like reducing everywhere. Now what I'm going to multiply with? I'm going to multiply this with my x vector. So this is like log n times n cross n 1, and I'm going to get this vector, okay? Now what does this tells us? This basically, each entry is basically whatever is here into this, So if I can prove that there is some s here where it has extracted exactly once, we will be very good, okay? But, so this is one matrix which is useful for us. But this tells us, this in your AB, this is B, right? This is what we would like to divide with, okay? So now we have to make another matrix, right? So what is another matrix we did? So you gave me this matrix A, because this matrix we formed randomly. Now what we do is that, what should you write here? Looking at A, you can write it, I want to get the index. What will I will write down the column numbers, right? What did you write here? 1, 2, 3, n. Now if there is some guy, just write down the corresponding column number, right? Right? 1 implies write down the column number. From A. There's nothing. This B is a deterministic matrix given A. Because B is random, A is random, so is B in certain sense, but I form B only after I have got my A. So there is no randomization in B. But let's try to see, I mean, what happens, right? What happens if we just had these two matrices, where do we fail? So just this is all that we keep. And now what I would like to say, because this was a successful attempt from us, so we say S passes the test. We say S passes test if A by B is in N, okay? I'll tell you. Okay, so now basically you have log n entries, right? I pretend all of this to be A, okay? And I pretend this into X, right, to be all of them be potential B's, okay? This is my potential, okay? What? Or okay. For each S in S0 S log n, I do the following. For each S, pretend that that is an S which is going to win me, okay? So what is this A? A is going to be summation J in S, Xj, Bj. This is a matrix. Like, look at that entry. This is my A. And what is my B? J in S, right? Xj. Right? That's it. So I'm pretending that this is the guy who's giving me this sum, and this is the guy who's giving me the index, right? So I don't know which one of them. I said if any one of them is fine for me, I'm fine with this, right? If for any one of them, and what did I say? When this S passes the test, if S passes the test, for each S, this is what I say, S passes the test if corresponding A divided by B, yes, is in 1 to n. This is what I would like to say.
Do we also need that this particular index in X is 1 or just.
What?
So do we also not need that this particular.
No. No. Look, this is an index anyway. This is an index anyway. A by B is going to be index. Right? Because what are you dividing with? Suppose this divided by this. It's not, I shouldn't write Bj, I should just write J. Because J in S, because this J into this, so this tells me this. Right? So what is A by B? Like A by B is going to, you take out J from here, right? Now if you were correct that this guy is only 1 at one index, then clearly this value is equal to some B, which is some particular entry, right? And this guy is like jth of that, okay? So this is it, okay? Now let's try to compute what happens. What is the claim? Our claim is B by 8th entry of X is A. This is exactly what you are saying. Sorry, what am I writing? A by bth entry of X is B, which is greater than 0. Clearly, because otherwise it would have been 0. Right? Okay, let's try to do. Okay, let's try to do some probability computation. Yeah. No, I'm not assuming any X to have unique entry. X is anything. Log n many? No, I'm not assuming. I was just to give you an intuition that if you had log n many round, where it will be captured? It should be captured in that particular S0 where the number of ones is exactly more or less equal to the number of ones in your X. Right? If it would have been all ones, then this is the guy who is going to capture this. Is this the guy who is going to capture this? No, you go little much more downer, he is going to capture one of these entries. So something of this nature. Okay? So now I would like to prove a lemma, and then we will see what we need to do. Otherwise, like, okay? Okay, here's the lemma. Let A. Look, I'm going through each S. There are so many A's. If I pass for one, then I just output that. Now for each S, I get A and B. For each S and this, maybe I should say AS or BS, maybe if you like to. Right? So for each S, I do this. Okay, maybe I should say AS and BS. S passes the test if corresponding AS, BS. If that makes it cleaner. Okay, but I would like to prove the following. Let A equal to I in n and xi is not equal to 0. This is precisely those indexes, right, which is not equal to. So this A be the position of non-zero entry, be the position of non-zero entries of X. What matrix A? Okay. Let's call it I. Index. Okay. Okay. So first thing, if I intersection S is 1, if I intersection S is 1, then S passes the test with probability 1. Then S passes the test, and this you will pass with probability 1, right? and what x a by s divided by b by s is a non-zero entry, right, is equal to what? Did I write correctly? Yeah, is Bs. This is correct, right? So this is the first property I would like. Second property which I would actually like to prove, and this is where we will have to do maybe some hard work. If I intersection S is not equal to 1, okay, then S does not pass the test with high probability. First one is obvious, right? If A intersection S equal to if I intersection S equal to some j, like there is some j, then what is AS? What is AS? J times xj. This is exactly what it is, because this is what it is, right? And what is BS? Is xj, right? So clearly we will pass the test and everything. If A intersection S is greater than or equal to 1, you don't want this guy to pass the test, right? How do you ensure that this doesn't pass the test? It could happen that you got some number, right? You got some number, you divided by this. Yes, it belongs to one to, it could be multiple, this, that, anything. How do we avoid this? You see my point? I could just be multiple for all that I care. And, right, I sum them, this is like 4, and the other guy is 16, right? And I divide and then I go belong to this. So, to handle these kind of things, what you do is you introduce a third matrix, okay? And what a third matrix is? This is a random matrix. But third matrix is formed using the matrix B. So say C. What does C does? So it picks a random number R. I'll tell you what is the range of this, right? It will be some poly in N, okay? 1 to poly in N. And I will tell you why it is interesting that this will work now. And now what I do, 1, 2, 3 up to N, right? And here what do I put? R to the power B I J. So what did I do? Basically look at what did I put here? Some column number, right? And what did I put here? R to the power column number, and that's it. But C is not any matrix. C is a random matrix in the following sense. Entries are not random, entries are deterministic, but what value I am going to get, and why am I doing this? You will see. Why am I doing this? To avoid all these multiplicities and this and that. That is because I want to say, look, if you become 0 like this, then this is like some polynomials, like it is like, it must be root of some polynomial which has small number of degrees. So if I choose large enough random object, then chances that it will happen is very low, okay? But now I need to change my test object also, okay? So R is a random value between some 1 to p minus 1, where p is some poly n, okay? So now I had a notion of AS and BS, okay? I can also define a notion of CS. And what is this? What should be CS? Simple, right? J in S. I am multiplying that row with this. So what will I get here? R to the power j xj. Right? and we will do this mod p arithmetic, okay. So we will write down mod p, okay. Now I say that S passes the test if this U passes this test, and C, what should be the CS? What is CS? Can you say what is CS? BS and R power what? What? AS by BS. CS. So I look at my BS, right? Because that is this, and I multiply with R AS to the power BS. Okay. If C is equal to this, right? So you compute this and this, right? And what you say? Now you say if S passes the test, if you pass both of this test, and so pick a passing S and AS base of entry greater than 0, okay. So if S doesn't pass, if none of these S passes the test, you say fail. But now let's look at what happens, okay. First thing holds irrespective of what we did before, but now let's just try to see what happens if I intersection S is greater than 1. I can think of this as a polynomial f of z summation j in S xz z to the power j, right, minus bj b z, and what is the power there? A by b, right. So it is AS divided by BS mod p. If it is more than this, then you get this, okay, and it's a non-zero polynomial of degree at most how much? Non-zero polynomial of degree at most capital N, because right. Now, why did you, I mean, you would have failed because you were equal here, right? You were equal here and you were equal here. This is why I failed, right? It means this guy has to evaluate at 0. This polynomial has to evaluate at 0. Why did you fail? You failed because you said, look, CS is equal to this, but what is CS is this, right? Now, what is R? R is a random, so let's put that as Z to the power Z, because I can choose Z, right? So then I can think of then I can think whole of this is nothing but a polynomial in Z, and this guy is going to be 0 only when this polynomial is going to be 0, whose degree is at most n. So how many such roots are there? At most n, right? So if you choose poly in n size field, probability that you have chosen R so that this is going to be 0 is very low, right? Like probability of failing is like n over n power 100, for example, because there are only n roots where you will fail. So probability that you will pass this test is 1 minus 1 over n to the power 99, right? So what did we learn from this? We learned from, so this is a geometric sampling. This is what I meant by geometric sampling. So now, so look, this 2 was there to tell us what object it is, and what was this for? This was to tell us which index it is. But now, and what is this R tells us that look, if you are going to do this multiplication, multiplicates and all this, then by choosing this R, I have taken care that you will not be equal, right? So this is where the randomization kicks in, right? Because up until now, I mean, yes, there was a randomization a little bit here, but here it was not a randomization. Okay, so what did we learn from here? Look.
Theoretically, you want the test to pass even when x is multiple ones for your zero sampling.
Yes. So up until now, what did I prove to you? That
You haven't gotten that matrix yet.
which matrix?
A.
No, no. This is my A. I have got my A. No. So think of this as a. I shouldn't be calling this as a. What this matrix should?
There you put log square and rows.
Yeah. We'll get to that log square. Like eventually we'll get to why to do this, right? But here if you notice there are like log n, log n, log n rows, right? So this is this matrix will consisting of, let's say, I don't know what to call this matrix, say D, right? So your A is, you first take your D, okay, or first you take your B, D, C, right? This will give you B, will give you A, this will give you C. So this is what it is, right? So this is my current matrix. It has a property, and what property did we prove this? That look, if there exists some S, then it will pass the test. If S intersection index is 1, then it is definitely going to pass the test with probability 1 in this. If some S intersection index is more than 2, that guy is going to fail this test. But we should say there exists some S whose intersection with I is 1 with very good probability. Only then it is useful thing. So that is the last thing that I need to prove to you, that there exists some S for which S intersection index is going to be 1 with good probability. Okay. And then we can stop. Okay. So is the goal clear now, right? What did we show? So again, with very high probability, but that is not what you will show. You have to choose your S appropriately based on how many entries here. Because again, what you want, like you want the collision to be just exactly 1, right? So you just cannot choose this, because you go here. What is the chance that you will hit exactly the same place where you were 1? That is also very low, right? Okay, so this is my A, this is what we proved, and this is basically PIT. Now what I would like to show that maybe not. Here's the lemma. Probability that I intersection S is 1 is at least 1/8 for some S, right? Because S is random, so A intersection S is also a random variable. Okay, so what is the proof for this? We have to choose I appropriately. Okay, pick I such that cardinality of I is more than 2 power I minus 1, less than 2 power I. Or let's say 2 power I minus 1. Okay, pick I such that this happens. What is the claim? I'm going to claim to you this Si is 1. Is this. So this is equal to what? Summation I intersection Si is 1. So I told you which S is going to work for you. So I choose and look at I, look at how many entries it has. It has between 2 power I minus 2 and 2 power I minus 1, and I just went and go ahead and chose Si. How did you select Si? Remember, it was with probability 2 power I. So this is going to be summation over j into I, okay? Probability j is in Si, right? So I want I intersection Si to be 1. So it could be any one of the index, right? So this guy exists, others do not exist, right? So j is in Si and k in k. Okay. So probability that j is in Si and k is not in Si for all k in I minus j. Agreed? So this is equal to j in I. What is this probability? Look, how did we pick up this? How did we pick up this Si? We put 1 or 0 uniformly at random at that place, right? So each of those places were independent. Like if I think of each entry, that is an independent event. So probability that this exactly this happens is going to be 1 over 2 to the power I times 1 over 1 minus, and I do not want others to happen, is equal to I minus 1. Do you agree to this? This is exactly what it is. Okay. Now we will have to do some okay, is this statement correct? Okay, I mean, so okay, so let me do some rough calculation because I really don't know how to do this exact computation. But look, can I write like this? Look at this. What is the bound on I? 2 to the power I minus 2, right? 2 to the power I minus 2. Do you agree? Okay. So summation j in I 1 over 2 to the power I, right? I can write this 1 minus 1 by 2 to the power I. Maybe I cannot write this. No, but I can definitely write down, but I is this. Right, you can write this. This is definitely correct. Minus 2 it is because it's like less than 1, right? So you can only upper bound by lower term. Okay, fine, I minus. Because there is also I minus 1, right?
You instead of I minus 1, you wrote I minus 2. If that
This number is less than.
No, but look, this 2 to the power I minus 2. Doesn't matter, right? Plus minus 1. Okay? So this is like roughly 1 over 4. 1 over 4e, e power 4. Because, do you agree this is like 1 over e power 4 because like 2 power I minus 2 into 2 by 2. Yeah, it is correct, right? I can write this as
2 power I by 4.
2 power by 4. Index point, right? This I can write the 2 power I by 4, right? So this is going to be 1 over e power 1 over 4, right? E power 1 over 4. I mean, you can do much better, but I'm just doing very bad. And this is like how much? At most 2. Half, right? No? So which is like 1 by 2, 1 over e to the power 1/4, which is like some constant. I'm like, okay, I mean, okay. But this is a constant probability of success, right? How can you improve this? This is where you use the fact that you want to improve this. So you do it not one time, 2 times, you have to do it several times to boost this probability of success to what do you call, to some 1 over 1 by poly n, because that is what is required. So to boost this probability, basically you are going to run this several times, like poly log n times, and then you can achieve this, okay? So please remember, like the only thing which I will, is a take home message from the today's lecture, at least this part of the lecture, is that there's something called geometric sampling, and this is what is called geometric sampling, and basically you take a matrix, right, and your objective is to just extract only one entry from these things and index, and we can achieve this with very high probability. And next time I will tell you how to look, but what I have told you to achieve this matrix A is not useful for streaming algorithm yet, right? I mean, it's way huge a matrix, right? I mean, so what I mean by streaming algorithm, one way I could have done in the beginning, and maybe one can do this. So notice one thing. In the streaming algorithm, when edges are, so now suppose if our goal was to convert this communication protocol or this communication algorithm to a streaming algorithm where edges are inserted and edges are deleted. So what will I do? For every vertex, I'm going to maintain an L0 sampler. What is the meaning of this L0 sampler? It means if there exists an edge in the already gone whatever it is, if there exists a set of edges there, then it is going to return you an edge with very high probability, right? So at every step of this algorithm, it is going to do something to this sketch, right? So what it does is that, oh, if some edge has come, it adds +1 or -1 at the corresponding A and corresponding A big EIG and sums this up. If something is deleted, it just does very little modification to this A matrix and achieve this. But keeping this A matrix, we can do all these things, but this A matrix is very bad. In the sense, it is very huge. So if I'm hoping to use just n poly log n space for my connectivity algorithm, right? I would like to say that, okay, here's a sketch, whether graph is connected or not, you can just look at the sketch and run your Bourbaka's algorithm or whatever algorithm and check. Then I cannot keep this whole big matrices because they're too huge for me to do this. So there has to have some implementation of these matrices where I only store a few numbers and I can get this sketch, this x tilde vector, by not together but like in a very nice fashion, right? So basically I know this whole matrix where the ones are, the zeros are and everything, in some sense I know, or I can toss a coin at that point of time and evaluate its computation and keep objects there. So most likely I'll give you a lecture on Thursday 3:30 just to fill up for my last lecture. I will send an email if I'm prepared, where I will teach you how to do L0 sampling in small space and then apply that L0 sampling in small space to give you a streaming algorithm for connectivity where streams, edges can both be inserted or edges can be deleted. So it's like a dynamic edge streaming, okay? So that's the goal of the next lecture.